Okay, so now we're doing Hall logic. Question 4a. Specify a precondition P and a postcondition Q such that the Hall triple PSQ holds precisely for all programs S that never terminate. Okay, so when is a Hall triple valid? When P and S terminates implies Q. So I want this to only be true when S never terminates. So I want to choose P and Q such that this thing's logically equivalent to not S terminates. Okay, well the only way an implication can be false is if this part's true and this part's false. So if we choose P to be false and Q to be true, then the only way this whole thing is valid is if this thing fails. And the way, oh, hold on a minute. No, we want this to be true and this to be false. I'm sorry. There we go. So the only way true and something implies false is if the something itself is false. So it looks like we can choose P to be true and Q to be false. The working out's not necessary, it just said state it, so that alone is a perfectly valid solution. Now let's move on. The following is a piece of code that computes the quotient and remainder of by after doing division. Yeah, okay, cool. We wish to use Hall logic to prove something, blah, blah, blah. Okay, given the desired post condition, what is a suitable invariant I for loop? Okay, so we want to prove loop. What's loop? Loop is the loop code. Okay, so this whole thing here is loop. And if we want to prove loop to be true, I need to work out what invariant to choose. So my post condition is this. My precondition, well, what's the best precondition I can cook up? Probably R is X and Q is 0 and R is greater than or equal to N. I guess that's going to be true before the code runs. That's really all I'm going to be able to cook up, right? So my precondition is R is equal to X and Q is equal to 0. And I need this to imply the condition. I need the pre to imply the invariant I. I need the invariant I and the code has stopped running to imply the post condition, X equals NQ plus R. I need to be able to prove the damn thing. I need to prove I and B run the body I. That's the magic 3 rules you got to check, right? So rule 1, rule 2, rule 3. Okay, so I guess we'll just like run it and see what happens, right? That's how we work out the invariant. So before we run the code, R is X and Q is 0 and N is whatever. So maybe I make N, I don't know, 3. I'll just leave it as N. That's okay. And X is whatever it is. So R starts at X. Loop counter 0, 1, 2, 3, and so on. So what does it do? We decrement R by N. So this becomes X take N. Q counts up by 1. N doesn't change, X doesn't change. Run the loop again. Subtract off another N. X take 2N. Q goes up by 2. N stays the same. X goes the same. And so on until R greater than or equal to N is falsified. So what's our invariant? How do we relate these variables together? Well, it looks like X is going to be equal to R plus Q lots of N. Because we have X is X plus 0, X is X minus N plus 1 lot of N, X is X take 2N plus 2 lots of N, and so on. So it looks like this is our invariant, which just so happens to also be the post condition, which means this is sometimes a good thing to check for the invariant, but that doesn't mean it's always going to work, right? We've conjectured this is the invariant, but it's got to satisfy the magic rules. Well, clearly the invariant and not B implies this, because this is going to be strictly stronger than that. If R is X and Q is 0, does this hold? Sure it does, because it holds in the first column on my little table, right? If R is X and Q is 0, this falls away, and that works. And is this thing provable? Probably, yeah. I mean, it seems to be an invariant. It seems to always hold for the loop. So this will be provable. We're going to have to show this later on anyway, right? So I conjecture the invariant is just x is equal to r plus qn. Maybe I'll write it the same way as this to make it easy. nq plus r. Okay? You don't need any of these little tables and stuff. If you just stated that, that's 4 marks. Of course, how do you come up with this? You've got to draw the tables. Okay, cool. What's next? Prove that your answer is indeed a loop invariant. Okay, this is a pretty lengthy question, so we'll go through it, and I'll make a new video. Yada yada yada, so we need to prove this property here. Okay, so I guess I'll write that down the bottom. So x is equal to nq plus r. The body of the code, what's the body of the code? The body is just this little part here. Okay, so we have r is assigned to be r take n, q is assigned to be q plus 1, and the post condition is also the loop invariant, x equals nq plus r. Okay, how am I going to prove this? I guess we just do the sequencing thing we normally do, right? So I have x is equal to nq plus r, q is assigned to be q plus 1, then do assignment rule backwards. X is equal to nq plus 1 plus r. Copy this precondition to be in my post condition for the other term. X is equal to nq plus 1 plus r. R is assigned to be r take n. And then I need this to be the precondition for this term here. So that way I can do sequencing. X equals nq plus r. Is this a valid form of the assignment rule? No, it's not. So I guess I'll copy up the post condition, do assignment backwards, and then make everything match. X is equal to nq plus 1 plus r. R is r take n. So replace the r's with r take n's. So x is nq plus 1 plus r take n. Is this the same as that? Well, if I expanded this out, I get nq plus n plus r minus n, and those two cancel, so we get nq plus r. Yeah, cool, that looks like it's the same thing. So x equals n, q plus 1 plus r take n is logically equivalent to x equals nq plus r. And there we go. So now I put in my line numbers and put in my rules. So this was assignment, this is logic, 1, 2, 3, 4, 5. Line 3 was precondition equivalence on 1 and 2. Line 4 is assignment. Line 5 is sequencing. Lines 3 and 4 connected together. Cool, there we go.